Hello, DataCon LA. I'm Mark Jackson, the Senior Quantum Evangelist at Quantinuum. I'm sorry that I couldn't be there in person to join you, but I would like to spend the next several minutes talking about quantum computing and how it's the next new technology in computers. So I'm going to go ahead and share my screen here. And I think you should be able to see that. So I'd like to talk about four different things. The first is about Quantinuum, the company that I'm with, and why it's so special and why we're going to be the leaders in quantum computing. Then I'd like to talk about the hardware that we've been developing. Then the Ticket software development kit, and this is primarily aimed at those who are already doing quantum development. And then finally, some of the commercial application software that we've developed, because some of you might be interested in some sort of collaboration. So Quantinuum is the recent merger between Honeywell Quantum Solutions and Cambridge Quantum. And we're a very unique company for several different reasons. We are the largest quantum computing company in the world. We have about 450 people spread all throughout the world. We're an American company, but we have offices primarily in the UK. We're also the only company in the world which has an integrated quantum hardware and software combination. And so we have significant teams in both of them. We have had a number of technical achievements. So we have the highest confirmed quantum volume, which is sort of the metric for how powerful a quantum computer is. We are the first to do real-time quantum error correction. We have the highest fidelity, meaning the lowest error rate of any qubits or quantum bits in the world. We open sourced the leading quantum software development kit, Ticket, and I'm going to talk a lot more about that in a few minutes. We have an open source Lambeck quantum lateral language processing toolkit. We have the first commercial quantum applications in both cybersecurity and chemistry. And I'll be talking about each of those. And so again, we are a very special company. In terms of what we actually build, it's applications. So we are not interested in consulting or advising. We're really only focused on building applications which will make a difference in the next few years. So we've worked with a number of companies in several different sectors. These applications have depended upon quantum algorithms in cybersecurity, chemistry, AI, and machine learning. These are all in turn dependent upon Ticket, which again is the software development kit, which I'll be talking a lot more about in a few minutes. And then we run our software on either our quantum computer or sometimes third-party platforms, whichever is best suited for that particular project. To tell you a little bit more about our quantum hardware, so we use ion trap technology, and it actually looks something like this. So an ion is really just a charged particle, and we can manipulate this using electric and magnetic fields. And we have now made significant advances in building quantum computers based on this technology. So the quantum volume, as I mentioned a few minutes ago, is sort of the single estimation of the power of a quantum computer. And over the past several years, we've been able to increase this by a factor of 10 every year. Now, you're probably familiar with Moore's law, which has shown over several decades that classical computers have doubled in power every 18 months or so. So you see that quantum is on a much faster trajectory than classical computers ever were. And this is why we think that we could have commercial applications in just 3 to 5 years. So it is not at all too soon to be getting into quantum. Many companies have been getting into this. And so since it takes a few years to actually develop the expertise and the quantum muscle, if you will, these are the companies that will most benefit from quantum computing when the first applications are being unveiled. So we have a very aggressive roadmap for how we're going to get scalable quantum computing. Right now, we have the H1 model, but later this year, we expect to be unveiling the H2 model. So this has a racetrack topology there compared to just the linear approach that we're using right now. Over the next several generations, we will be having a grid and then integrated optics, and then finally large-scale scaling. And so this is when we'll really have the very powerful quantum computing. But again, we already have a roadmap in which we think that this ion trap technology will get us there. To tell you a little bit more about Ticket, the quantum software development toolkit, so right now we have several different technologies that we use for building quantum computers. So I mentioned that we happen to use the ion trap method, but there's also the superconducting approach and the photonic approach and several other various technologies. And there's many groups and companies and some academic groups which are using these different technologies. And on the other side, we have several different applications. And of course, these all depend on writing quantum algorithms. Ticket is sort of the glue that keeps these together. So Ticket takes your code and allows you to run it most efficiently on whatever platform you would like to run it on. We have been developing Ticket for several years, and as of this month, we have had almost 500,000 downloads. So it is a very popular tool that many people have contributed to. To see how much more universal Ticket is compared to other platforms, this is a quick comparison showing how Ticket allows you to use almost any quantum platform to run your software, whereas most of the other software development kits are pretty limited in which platforms they would allow support on. So in terms of how Ticket does this optimization and allows you to run your circuit as efficiently as possible, there are two different components to this. The first component is optimizing just the circuit itself. So this is independent of the hardware that you may have chosen. And the second component is specific to the hardware. So it takes into account all the constraints of that particular platform. Focusing now on this first part. So when it optimizes the circuit, it first does what's called people optimization. So it looks just locally at the different operations on your circuit, and it looks for different patterns that it can replace. And the second component is more macroscopic, and this is especially useful for chemistry circuits. So this is a typical quantum circuit. So the horizontal lines there are qubits. You have different operations, and then finally at the end, you have the measurements acting on the qubits. So you would feed this in as the input to Ticket. And what Ticket will do is it will look at these different combinations of gates for different ways that it can simplify. So the simplest example is there on the upper left-hand corner. These are two CNOT operations in a row. And of course, mathematically, this is identical to nothing. So this means that Ticket will just remove those two gates and replace it such that the qubits are untouched. So this means your program runs a little bit faster and it's a little bit less likely to make an error. These other operations here are less obvious, but if you had some time on your hands, you can check that indeed they're mathematically identical and they're less likely to give you an error. If you're curious about the mathematical underpinnings of this, I've listed the archive number explaining all the theory behind this. So the second component is solving the constraints which are specific to the hardware or platform that you're using. And there's a few different components within this. So the first is the qubits mapping. So this is how the qubits are physically connected. Then there's the gate translation, because the gates which are native to that platform aren't necessarily the gates that you might be using in your circuit. And then finally, some platforms allow mid-circuit measurement. And if this is the case, then Ticket can automatically take that into account. So to understand why this might be important, these are three different superconducting platforms by Google, IBM, and Rigetti. And even though they all use the same superconducting technology, you see that the way that the qubits are connected is very different. And furthermore, the basis gates there listed at the bottom, those are very different. And of course, these aren't necessarily the gates that you would be using in your circuit. So Ticket will automatically do all this conversion for you. And to see an example of how important this might be, the circuit on the right, this is an example of a 5-qubit coupling circuit. So you see that the 2 qubits on the bottom, they have 5-qubit couplings there. This architecture on the left, this is the IBM Melbourne machine, and it has 4-qubit couplings at most. So naively, we might think there's no way to run the circuit on the right on the machine on the left. That's actually not true. We can do it, but we have to be a little clever about it. We have to do something called routing. So routing is when you perform the swap operation. You're switching the information between 2 qubits. So in this way, you can move the information around the qubits so you don't have this limitation any longer. Swapping is a perfectly legitimate operation. You do it by introducing a few CNOT gates, like they're shown on the bottom. But of course, adding more CNOT gates is what we don't want to do. This makes the program run longer, and it's a little bit more likely to make an error. So we don't want to do this swapping unless we absolutely have to. Ticket has a built-in heuristic optimizer, so it will find the most efficient way to map your circuit into the platform that you've chosen, taking into account all of this topology. Obviously, we use Ticket for our own internal development, but many other groups have been using it as well. These are some articles which have been written by Google and IBM and even CERN, the Particle Physics Laboratory. And in almost every case, they found that their circuits ran faster and were less likely to have errors introduced. And so again, I strongly encourage you, if you are a quantum developer, to use Ticket. These are some independent benchmarks that were recently done comparing Ticket to other compilers. And again, in almost every case and on almost every platform, Ticket was the better compiler and SDK. We are constantly updating it. And there was a major upgrade last September in which we made it completely open source. So not only is it free and without any licensing restrictions, but every line of code is now available. So you can inspect exactly how Ticket works. If you have some clever idea that you'd like to contribute, you're absolutely welcome to contribute. If you have your own hardware group and you'd like people to run circuits on your quantum machine, you can write your own extension. We are obviously adding some features in the future. We have an error mitigation toolkit called Kermit coming up. We are in the process of moving it to the cloud. So right now you download it from GitHub, but we will soon have a cloud version, which makes it easier to collaborate. It's easier to work with cloud platforms like AWS and Azure and things like this. And we are already adding features so that the next generation of quantum hardware, such that it includes quantum error correction, will automatically be incorporated into Ticket. This is how you download it. So if you'd like to take a screenshot there, this is the GitHub repo where you can download Ticket, and this is the Python interface for this. There is lots of examples and notebooks and documentation to help you get started. You use the usual pip install to do this. So again, if you're a quantum developer, I highly encourage you to use Ticket. The final thing I want to talk about is the software that we've developed with some of our commercial partners. And this is really our main area of expertise, is producing applications which will use quantum technologies to benefit these problems in the next few years. So we really are focused on short-term things that we can do with quantum computing. We're not thinking about what might be possible in 20 years. So one project we had was with JSR Life Sciences and Crown Bio, in which we used quantum machine learning to look at the correlations in biomarkers and genes and how effective different oncology drugs are. And of course, this could really improve oncology drug efficacy predictions. Eventually, it could revolutionize medicine in this way. There's a lot of interest from financial groups in quantum computing and specifically quantum machine learning. So the main technology in this is what's called Monte Carlo simulations. So Monte Carlo is a way of modeling so-called random or uncertain processes like the stock market. It turns out there's a quantum Monte Carlo algorithm, which was believed to be quadratically faster than its classical counterpart. And it was actually our scientist, Stephen Herbert, who confirmed this last year. And so we've had several projects with financial institutions developing this quantum Monte Carlo and applying it specifically for trading algorithms. We've had a few different optimization problems where we used a quantum computing algorithm to find a more efficient way to do something. One project was with Nippon Steel. In their production line, when they actually make the steel on the assembly line, there's of course a lot of different steps that are involved. And we worked out a more efficient way to do this using a quantum algorithm than they had done using classical means. And a similar project was done with Deutsche Bahn, the German rail company. And so we took a simplified version of their train schedule and found a more efficient way to do this, again, using quantum algorithms. As I mentioned earlier, we are the first to unveil a quantum chemistry application. And so chemistry is actually one of the main applications of quantum computing. It was one of the first reasons why quantum computing was developed. And the excitement here is that classical computers are almost completely unable to do molecular simulations. They can only do it for the very smallest systems. And it's at about 100 electrons that we can actually start to tackle industrially relevant systems using quantum technologies today. We've had a few dozen projects in quantum chemistry, and every time we did a project, we added one feature to this application in Quanto. And about 2 months ago, we unveiled this. So it is now available for commercial use. If you are a computational chemist, you can use in Quanto, but you don't need to be a quantum computing expert. So if there's some sort of technical bottleneck, which is preventing you from making progress in some problem in chemistry, we would love to talk to you about using in Quanto for this. Some of the projects that we worked on before that were fed into in Quanto include a project with Total, the French energy company, in modeling carbon capture on metal organic frameworks. We had another project with Nippon Steel in modeling iron crystals with novel noise mitigation. And we also had a project with Roche in modeling protein ligand interactions. And this was applied specifically for a potential drug for Alzheimer's. So again, these are very real world chemistry applications that we are already starting to use quantum computing for. The final thing I want to talk about is cybersecurity. And this is probably the one thing that you might have heard about quantum computing, is that it has something to do with cybersecurity and hacking and things like that. And there is a good reason for this. It turns out that the encryption methods, which were developed several decades ago, happen to be vulnerable to using quantum algorithms. And so for that reason, there is a very real threat to a lot of encryption methods, including RSA. And that's why we strongly encourage you to upgrade to what are called post-quantum encryption algorithms. And there's a lot of interest and publicly available information. There's a government contest going on right now in which they've identified a few finalists. So again, I would encourage you to upgrade to post-quantum encryption if you're in a position to do so. One thing that is often overlooked in encryption is the keys. So recall that a key for cybersecurity is a long string of numbers which are used to perform the encryption or decryption. And something that people often just take for granted is that these keys are safe. They might look at the keys and think, well, this seems random enough. I'm sure it's fine. But the truth is that most keys generated are only pseudo-random. If they were generated with a classical computer, they're only pseudo-random, which means there actually is a pattern, even if it isn't obvious to you. And there have been instances in which people have anticipated what that pattern is and cracked the encryption based on this. We have developed a way of producing provably secure keys using quantum computing. So what we did was we produced a quantum circuit, shown there on the upper left-hand corner, where we run the circuit and it produces entangled pairs of qubits, which allow us to perform a Bell test. So this is a mathematical statistical check on the entanglement. And as long as the entanglement is still there, it means that the randomness is true and there was no tampering or eavesdropping going on. And if that's the case, then the output is just cryptographic keys, which you can use for whatever cybersecurity protocol you have. This has moved beyond the research and development phase and is actually now being commercially deployed. So this is an actual commercial product that we have already released. There are companies which are already using this to produce provably secure keys for their encryption system. And so if you're interested in this, I'd be glad to speak with you more. So that's a very quick summary of quantum computing and why this is the next new technology in computing. Again, my name is Mark Jackson, and I'm the Senior Quantum Evangelist at Quantinuum. My email address is shown below. So if you're interested in learning more, I would love to speak with you. Have a great day.